The experiment is making some nervous that it could create a cosmic black hole.
In the depths of the Swiss countryside, concealed beneath the Earth, a colossal scientific marvel has been quietly rewriting the laws of the universe. For the past decade, the Large Hadron Collider, the greatest experiment of our time, has delved into the mysteries of the cosmos, unlocking the secrets of the smallest building blocks of existence. From the fiery birth of our universe to the enigmatic nature of dark matter, the Large Hadron Collider has become a portal to a realm where ordinary rules cease to exist. Now, as we celebrate a decade of unparalleled exploration, we embark on a journey like no other. Join us as we dive deep into the catacombs of knowledge, traversing the infinite wonders and mind-bending revelations that have been uncovered by the Large Hadron Collider. Large Hadron Collider, the biggest and most powerful particle collider, known as the Large Hadron Collider, LHC, was constructed by the European Organization for Nuclear Research, CERN, from 1998 to 2008. It was a collaborative effort involving over 10,000 scientists, hundreds of universities, and numerous laboratories from more than 100 countries. The LHC is located in a 27-kilometer tunnel situated around 175 meters below the France-Switzerland border near Geneva. In 2010, the LHC achieved its first collisions, reaching an energy of 3.5 tera-electron volts per beam, which was nearly 4 times higher than the previous world record. After subsequent upgrades, it reached an energy of 6.5 tera-electron volts per beam. The collider consists of 4 crossing points where accelerated particles collide. 7 detectors are strategically positioned around these crossing points to detect various phenomena. The primary purpose of the LHC is to enable physicists to test predictions made by different particle physics theories. One of the main objectives is to measure the properties of the Higgs Boson and search for new particles predicted by supersymmetric theories. The term hadron refers to subatomic particles made up of quarks held together by a strong force, similar to how atoms and molecules are held together by electromagnetic force. Examples of hadrons include protons, neutrons, and mesons like the pion and kaon. A collider is a type of particle accelerator that brings 2 opposing particle beams together to collide. Colliders are essential tools in particle physics research as they can reach higher center of mass energies compared to fixed target setups. By analyzing the byproducts of these high-energy collisions, scientists gain insights into the structure of the subatomic world and the fundamental laws of nature. Many of these byproducts decay quickly, making it impossible to study them through other means. The LHC is housed in a circular tunnel ranging from 50 to 175 meters underground. The varying depth was deliberately chosen to minimize excavation under the Jura Mountains, avoiding the need for a vertical access shaft. This decision saved CERN from purchasing expensive surface land and had the added benefit of shielding against background radiation provided by the Earth's crust. The tunnel, lined with concrete, was constructed between 1983 and 1988 and was previously used for the Large Electron-Positron Collider. Ancillary equipment such as compressors, ventilation systems, control electronics, and refrigeration plants are located in the above-ground buildings. The data generated by the LHC and related simulations were estimated to be around 15 petabytes per year. To handle this massive amount of data from the collisions, the LHC designed a computing grid, which is an international collaborative project consisting of a network of grid-based computers. The construction of the Large Hadron Collider cost approximately 7.5 billion euros, making it one of the most expensive scientific instruments ever built. It was approved for construction in 1995 with a budget of 2.6 billion euros and an additional 210 million euros allocated for experiments. However, the initial testing of the LHC was delayed for 14 months due to a magnet quench incident that caused significant damage to over 50 superconducting magnets, their mountings, and the vacuum pipe. Higgs Boson. The first discoveries made by the LHC were significant. They included finding the Higgs boson, which is an important particle in physics. This particle was first mentioned by a British scientist named Peter Higgs in 1964. Back then, scientists were trying to solve a tricky puzzle. How do certain particles get their mass? It's not just about the particles in our atoms. Their mass comes from the energy of tiny things called quarks and gluons inside them. But what about bosons? They're responsible for the weak interaction and the decay of atoms. How do they have mass, too. That was a complete mystery. Peter Higgs had a bold idea. He thought that when these particles move, they encounter resistance from a mysterious field that exists everywhere in the universe. It's like walking on the bottom of shallow water. The deeper you go, the harder it is to lift your legs with each step. Other scientists found support for Higgs's idea, and they jokingly called both the field and the particle the God particle. Eventually, the Higgs boson became a crucial part of the standard model in physics. Generating it in an experiment became a matter of pride for physicists. The Large Hadron Collider became the first accelerator to collide protons with enough force to manipulate the Higgs field and create ripples of the God particle. On July 4th, 2012, two teams at CERN announced that they had found the Higgs boson. It turned out to be incredibly heavy, about 130 times heavier than protons. This means that the Higgs field has very high energy, even when it's in a stable state without any external charging. It's like turning off your Wi-Fi router but still being connected to the internet. It seems impossible, but that's what happens with the Higgs field. However, instead of providing Wi-Fi, it gives mass to particles throughout the entire universe, even in the emptiest spaces between galaxies. It's a godly field, but it has terrible consequences. The existence of the massive Higgs boson means that the vacuum of our universe is not truly empty. It's false. Even the darkest and emptiest parts of space are filled with background energy. This makes experiments at the Large Hadron Collider extremely dangerous for the entire universe. Now it's time for today's subscriber pick. A captivating photograph emerged, revealing a catastrophic event within the sprawling underground tunnels of the renowned Large Hadron Collider, or also known as LHC. The image depicted a mesmerizing surge of crackling energy coursing through the colossal machinery, stirring concern among its creators. This unsettling sight sent shockwaves through the global scientific community, leaving researchers with an uneasy sense of apprehension. Whispers spread like wildfire, evoking vivid notions of imminent peril. The LHC, once celebrated as a key to unlocking the universe's mysteries, had transformed into an enigmatic source of dread. As time passed, an abundance of theories flourished. Some conjectured that the LHC had inadvertently torn through the very fabric of reality, opening gateways to alternate dimensions. Others entertained the idea of a cataclysmic event capable of untangling the very fabric of the universe itself, sparking whispered discussions of an impending doomsday scenario. What are your thoughts on whether the LHC could be a serious danger that could potentially cause the extinction of humanity? Feel free to share your opinion in the comments section. Crack in Earth's magnetic field. Scientists at CERN just announced a terrifying new discovery. During the third run of the Large Hadron Collider, something extraordinary happened that left scientists puzzled. On July 7th, a crack appeared in Earth's magnetic field, and it didn't just disappear quickly like a flash of lightning. This mysterious crack remained open for a remarkable 14 hours, allowing intense solar winds to pass through and triggering massive geomagnetic storms. The result of these storms was a breathtaking display of auroras, those dazzling lights that grace the sky near the poles. Enthusiastic fans of science fiction even fantasized about the possibility of otherworldly creatures, like the monstrous villain from Stranger Things, emerging through this crack. Although that remains purely a dream, the geomagnetic storm caused by the crack did create a mesmerizing aurora that captured everyone's attention. But how did this crack come to be? It turns out that it was caused by a rare phenomenon known as a co-rotating interaction region, CIR, from the Sun. These CIRs are large-scale plasma structures formed in the region surrounding the Sun, called the heliosphere. When fast and slow-moving streams of solar wind interact with each other, they generate these CIRs, which eventually get propelled toward Earth. These CIRs can contain shock waves and compressed magnetic fields, leading to stormy space weather. The result, as we see it, is a magnificent display of auroras. In this particular case, the CIR hit Earth's magnetic field during the early hours of July 7th, creating a long-lasting geomagnetic storm of G1 class. Now, should we be concerned about these cracks in Earth's magnetic field? According to experts, there's no need to worry. Cracks in the magnetic field are actually quite common and serve as a shield against solar storms from the Sun. It is believed that these cracks open and close relatively quickly, but recent events have shown that they can stay open for several hours. However, the good news is that the crack did not cause any significant disruptions such as radio blackouts or power outages. Instead, residents of Canada and the US were treated to astonishing northern lights. Scientists have also revealed that the Sun is heading toward its most active period in the solar cycle, which has started much earlier than expected. This means that the chances of witnessing these awe-inspiring auroras will only increase over the next 3 years. Hadrons. In 2017, the LHC made some exciting discoveries based on the large amount of data collected in 2016. This discovery was related to the properties of the Higgs Boson, a particle that gives mass to other particles. Scientists studied the Higgs Boson in more detail, gaining a deeper understanding of its behavior. They also improved the precision of several other results obtained from the data. In recent years, the LHC experiments have uncovered 59 new particles called Hadrons. These discoveries came from analyzing the data collected during the first 2 runs of the collider. One notable finding was the observation of a new type of pentaquark, which is composed of specific combinations of quarks. As time goes on, particle physics experiments tend to yield diminishing results. To address this, scientists plan to upgrade the LHC to enhance its capabilities. This upgrade, known as the High Luminosity Large Hadron Collider, began in 2018 and aims to increase the luminosity of the machine. This upgrade will improve the chances of observing rare processes and making more precise measurements. The third run of the LHC, which is currently in progress and set to end in late 2025, is considered an intermediate stage. The first run was highlighted by the discovery of the Higgs Boson, while the second run focused on studying its decay modes. The third run aims to double the amount of data collected so far. After the third run, there will be a period of preparation that could extend until 2029. Then, the fully upgraded LHC will resume operations with collisions happening at a rate 10 times larger than before. The fourth run, estimated to last until 2042, will accumulate an enormous amount of data, almost 10 times larger than what is expected at the end of the third run. Rare proton collisions. The Large Hadron Collider is being used to study the fundamental particles and forces that make up the universe. It works by colliding protons together at very high energies and recording the results of these collisions for analysis. Protons are the particles of choice for these experiments because they are the easiest to handle and manipulate. However, protons are not elementary particles themselves. They are actually made up of smaller particles called quarks, which are held together by particles called gluons. These gluons are the carriers of the strong nuclear force. To better understand the collisions at the LHC, we can think of protons as bags of jelly beans containing quarks, gluons, and even heavier particles like the W and Z bosons. When 2 protons collide, the bags of jelly beans can be ripped apart, and the particles inside will reform into new protons, pions, and other familiar particles. Sometimes only 2 quarks or gluons collide head-on, releasing their energy back to the quarks and gluons or even to the heavier particles. Physicists study and analyze these collisions to get a glimpse of the laws of nature at incredibly short distances. As the LHC accumulates more data, the experiments keep building up larger and larger samples of these rare reactions. Scientists hope that eventually they will accumulate enough events to provide irrefutable evidence of new discoveries. Finding these rare collisions is a huge data challenge. Bunches of protons collide 40 million times per second in the LHC, and each collision can have 50 or more individual proton-proton collisions. The photographic evidence of these collisions captured by the detectors is written into permanent storage. Each picture is nearly 20 times larger than a typical smartphone photo. Storing all the evidence for just 1 second of operation would produce a 1,000,000-gigabyte database. To cope with this massive amount of data, the LHC experiments use a trigger system. The trigger is a bank of computer processors that selectively choose a few hundred collisions per second for permanent recording. This selected data will be analyzed by physicists. Despite this selective approach, the LHC experiments already constitute one of the largest computer databases in the world. The primary goal of the LHC is to discover new elementary particles that could provide evidence for new fundamental interactions. Some of these proposed particles could be heavy and would decay into clusters of quarks and leptons, displaying very high energy. However, scientists don't expect to discover such particles in the upcoming Run 3 of the LHC. At best, these experiments might provide some interesting statistical hints and suggestive event pictures with novel features. The high luminosity LHC in Run 4 and subsequent runs is expected to confirm these suggestions and make further discoveries. Dark matter. Currently, scientists are actively searching for new particles that could be related to dark matter. These particles are not easily detected because they are produced through weak and electromagnetic interactions, which have low rates compared to strong interactions. To overcome this challenge, researchers are looking for visible particles that recoil or move in response to the invisible emissions of dark matter particles. This is based on Newton's third law, which states that every action has an equal and opposite reaction. However, in many models, the partners of dark matter particles release only small amounts of visible energy, resulting in minimal recoil signals that often go unnoticed by the experiment's triggers. In the upcoming Run 3 experiments, improvements in the trigger systems are expected. These enhancements will increase the coverage for these subtle signals and help reduce a sample of rare events in which the recoiling particles are pushed out into an easier view. In other words, the improved triggers will make it easier for the detectors to recognize and capture these signals. The advancements in trigger systems will greatly enhance the ability of the ATLAS and CMS experiments to identify these signals. It will allow scientists to gather more data and increase the chances of finding the elusive new particles associated with dark matter. This is an exciting opportunity to expand our understanding of the universe and shed light on one of the biggest mysteries in modern physics: the circular collider of the future. Did you know that the European Organization for Nuclear Research is not just famous for its Large Hadron Collider? They are also working on exciting plans for a future circular collider, which could be the most powerful particle smasher ever built. This collider is still in the preliminary design phase, but it has the potential to revolutionize our understanding of the universe. Building the future circular collider will be a massive undertaking, and it's estimated to cost between 9 and 21 billion euros. However, not everyone is convinced that it's a good investment. Sabine Hosenfelder, a theoretical physicist, believes that there may not be new physics to discover at the energy levels this collider would reach. She suggests that the large sums of money could be better spent on other ambitious projects, such as placing a major radio telescope on the far side of the moon, or launching a gravitational wave detector into orbit. While these alternative projects may seem appealing, it's important to note that the LHC, CERN's current flagship accelerator, is still ongoing. It is yet to finish its third run and prepare for a fourth one. These upcoming runs of the LHC are expected to contribute significantly to our knowledge of particle physics. However, what is making this thought-provoking is the question of whether we might have yet to pay the real price of using the world's most powerful particle accelerator. Could it harbor a black hole or some other extreme substance that could potentially destroy the Earth? Or perhaps the very existence of the universe as we know it is at stake? The scientists and physicists who work with the LHC have made incredible scientific discoveries using the machine. However, there are concerns about the risks involved. Could the LHC be an Earth destroyer? But why do some scientists think the Large Hadron Collider could create a black hole and potentially destroy the Earth? The European Organization for Nuclear Research did not originally plan for the massive particle accelerator to function as a black hole generator. Initially, scientists had successfully developed the standard model of particle physics. However, practical confirmation was necessary. In 1968, experiments conducted at the Stanford Linear Accelerator demonstrated that protons are composed of 3 tiny particles called quarks, similar to neutrons. These observations led to the classification of these particles as hadrons. However, further research on quarks required a more powerful instrument than the 3-kilometer-long Stanford accelerator. Consequently, CERN embarked on the creation of the Large Hadron Collider, a colossal project costing $9 billion. The LHC consists of a 27-kilometer tunnel, 9 times larger than the Stanford accelerator, housing approximately 10,000 magnets maintained in a superconducting state at extremely low temperatures. Accelerating proton beams to nearly the speed of light and keeping them in close proximity, the LHC facilitates collisions with a minimum energy of 7 tera-electron volts, which is 140 times more powerful than the Stanford accelerator. To put it into perspective, the energy involved in LHC collisions is significantly smaller than what it takes to lift a cup of coffee to your lips. However, when the scientists began constructing the LHC tunnels near Geneva in 1988, some expressed concerns about the potential negative effects of these collisions. Renowned astrophysicist Martin Rees suggested that the LHC could create quantum black holes. These black holes wouldn't form due to mass accumulation like typical black holes, but rather from a high concentration of energy in a small space. Stephen Hawking himself had predicted the existence of such microscopic black holes, but he later contradicted Rees, stating that the energy from proton collisions in the LHC was trillions of times lower than what would be required to form a quantum black hole. The standard model of particle physics supports Hawking's argument, but Rees pointed out that alternative theories proposing even several giga-electron volts could lead to a catastrophic event: quantum black holes. The media described a dramatic event where a quantum black hole suddenly appeared near Geneva. It was said to devour all of Europe within seconds. Just a minute later, a regular black hole replaced Earth, but it was only 3 centimeters in diameter. However, none of that actually happened. In fact, according to one theory, a quantum black hole is not capable of sucking anything in. Instead, it is supposed to instantly evaporate and release a powerful wave of Hawking radiation. In a series of tests on September 19, 2008, there was an incident at the Large Hadron Collider where 100 magnets overheated simultaneously, causing a significant leak of 6 tons of helium coolant. Fortunately, this only affected the magnets themselves, and no staff members were injured. However, it led to extended maintenance, postponing the launch of the LHC by over a year. Although some might speculate that the accident occurred due to the explosion of a microscopic black hole, it is highly unlikely since no similar incidents have occurred since the collider's launch in 2010. Either nothing of that sort has happened again, or certain physicists have hidden the creation of quantum black holes to prevent panic while ensuring the safety of the equipment. This could possibly explain the prolonged maintenance period. Personally, we are skeptical of such conspiracy theories and believe it is crucial to thoroughly investigate and address the safety concerns of the LHC. However, it's important to note that black holes are not the most destructive outcomes the LHC could produce. Big Bang recreation. The Large Hadron Collider experiments aim to recreate the conditions of the Big Bang here on Earth. Physicists want to recreate the powerful explosion that gave rise to our universe. In the first 10 microseconds after the Big Bang, the universe didn't have its usual protons and neutrons. Instead, it was filled with a super-hot substance called quark gluon plasma, which was even hotter than the sun's core. Scientists decided to recreate this extreme substance in a series of experiments at the Large Hadron Collider, specifically the ALICE experiment. They accelerated large lead atom nuclei to nearly the speed of light, causing a powerful collision. This lead-smashing experiments began in November 2010, and by May of the following year, the ALICE team announced the successful creation of quark gluon plasma. While there were risks involved, the synthesis of quark gluon plasma in the LHC only resulted in energy bursts from a few atoms. The extreme conditions needed to sustain the quark gluon plasma state were not maintained, so it quickly expanded and cooled, forming particles. Therefore, there is no danger of triggering another Big Bang on Earth. However, the LHC collisions can also reveal other extreme properties of the early universe that could potentially have destructive effects at the atomic level. The immense nature of the Big Bang is not solely due to the explosion itself. Recreation of the inflation field. Cosmologists have a theory about a sequel to the Big Bang known only among them. Approximately 10 to minus 36 seconds after the expansion began, the universe was incredibly small, even smaller than protons and quarks. If it had continued expanding at the same rate, the universe would have been too dense and hot for any form of life. However, we were saved by cosmic inflation. Right after the Big Bang, the subatomic universe rapidly expanded to the size of a coin. This may not sound significant, but it's actually the difference between a grapefruit and the entire observable universe today. Inflation occurred about 10 to minus 32 seconds after the Big Bang, giving momentum to the young universe and preventing it from collapsing under its own gravity. However, scientists are uncertain about the cause of this inflation. One theory suggests that a special inflation field containing a particle called the inflaton played a role. The field quickly charged the inflaton particle, causing the universe to expand. It's as if the inflaton slid down an energy slide and disintegrated, potentially resulting in the fragments from which quark gluon plasma emerged. If we could infuse the inflaton with energy, there's a possibility of turning back time and resurrecting it. Whoever achieves this in the Large Hadron Collider would likely win the Nobel Prize in physics. However, the consequences could be severe. Once revived, the inflaton would likely seek to have some fun, similar to the early days of the universe. It would slide down its energy slide again, instantly inflating the surrounding universe. This would create vast new spaces underground near Geneva, potentially reaching the size of Earth or even the entire solar system. Needless to say, such an inflation bomb would destroy our planet. Scientists at CERN claim that their project cannot bring the inflaton field back to life. The best or worst outcome the Large Hadron Collider could generate is a milder form of inflation in a lower section of the energy slide, resulting in less extreme expansion of space. However, the exact parameters of the inflation field remain unknown, and there is a possibility that it was so powerful that even in its final moments, it could leave behind an enormous crater where Europe currently exists. Personally, we would rather forego the Nobel Prize and keep the Earth intact. Furthermore, certain physicists have already sought to discover another remarkable particle with equally dangerous capabilities: Quark Substance. Experiments at the Large Hadron Collider might have a big effect on Earth and other places. Recently, astronomers found a strange neutron star far away from us, which shouldn't be possible according to what we know. The best explanation so far is that it's a peculiar star. Scientists at CERN are interested in this because they think under certain conditions, quarks can form something called strange matter, which is a very dense substance with low energy. But a physicist named Martin Rees warns that strange matter might not break down like other matter. Instead, it could form strangelets, which are bits of quark substance that could spread. A strangelet can make surrounding matter efficient and dense like itself. Rees is worried that if strangelets spread in the LHC, Earth could become a small planet only 100 meters wide. Strange stars were also once thought to be impossible, so we shouldn't quickly dismiss these concerns. There's even a theory that a global catastrophe already happened because of the LHC, and we barely survived it. So it's important to consider these possibilities and keep an open mind. Catastrophe and a new circular collider. Max Laughlin, a teenager of around 15 years old, is considered one of the smartest teenagers in the world right now by his fans. He founded a high-tech startup and knows a lot about physics. According to him, the experiments in the Large Hadron Collider caused a global catastrophe that affected everyone. It doesn't matter if it was a vacuum decay or a plasma explosion. The important thing is that survivors were unknowingly transported to a nearby parallel universe temporarily. Max Laughlin blames the Large Hadron Collider for the Mandela effect, where many people mistakenly believed that Nelson Mandela had died long before his actual passing. Thousands of people around the world thought Mandela died in prison in the 1980s and never became president. This phenomenon has influenced various things worldwide. For example, some believe the Monopoly game's mascot wore a monocle when he didn't. Others think Darth Vader said, "I am your father," in the first Star Wars sequel, even though that line doesn't exist. Many examples of the Mandela effect exist, and you might have experienced it too. Max's theory agrees with the idea that in quantum physics, each experiment makes new universes. Is this too unbelievable? What if the Large Hadron Collider accidentally split our universe, throwing us randomly into parallel versions of it? This idea gains weight because the Mandela effect happened after proton collisions in the LHC. By the way, was his name Max or Mark? Anyway, CERN operates the Large Hadron Collider, but they're not only focused on that. They want to build a new one called the Future Circular Collider. It'll be huge, 100 kilometers around, and collide particles with 6 times more energy. The challenge is getting $22 billion, but they want to finish it by 2050. They want to use it to test theories better, but it feels like we're also testing our luck in the wider universe. What are your thoughts on these incredible discoveries by the Large Hadron Collider? Let's have your answers in the comments below. Thanks for watching, and we'll see you in the next one.